So this video tonight is going to help you hopefully to understand the different calculations involved with the electronics of an atom. That is the electronic components dealing with the electrons. So I've come up with some pretty simple sample problems, use some resources that I had, and hopefully this will guide you through everything you need to know. So really what it comes down to is there's only a couple of equations we need to know. The first equation is c, speed of light, is equal to the wavelength of light times the frequency of that light. The second is to know that the energy of a photon is equal to h times the frequency, or is equal to h times the speed of light divided by lambda. And then the third thing that we need to know is that is called the de Broglie equation, and what that is that the wavelength of light corresponds to the mass and frequency, mass and velocity through Planck's constant. So the wavelength of light is equal to h divided by m times v, not to be confused with the frequency right there. So those are really the equations that we need to know, and we'll worry about which ones we need to know at which point in time here. Okay, so I've left this first one up because light near the middle of the ultraviolet region of the electromagnetic radiation spectrum has a frequency of 2.73 times 10 to the 16th inverse seconds. Yellow light has light near the middle of the visible region and gives us this frequency right here. Calculate the wavelengths that correspond to each of the frequencies. Well, a couple things we need to remember. First of all, c is always going to be equal to 3.00 times 10 to the 8th meters per second. Okay, 10 to the 8th meters per second. So what we want to know the wavelength that correspond to the frequencies, and we know the speed of light, so we know c, and we know frequency, so we're trying to calculate for wavelength. So a couple things. I like to do the arithmetic up front to understand that we're going to calculate the wavelengths, which are going to equal c divided by the frequency. And so now we've got, if we're dealing with the ultraviolet region, so we'll use purple for the first example, we know that the wavelength is going to equal 3.00 times 10 to the 8th meters per second divided by the frequency of that ultraviolet region, 2.73 times 10 to the 16th inverse seconds. Okay, and what we should be left with as unit is in terms of meters, because we got meters per second divided by inverse seconds. So when we come over to our calculator over here, we can see that we've got open parentheses 3.00 times 10 e to the 8th close parentheses divided by 2.73 times 10 to the 16th close those parentheses equals, we get about 1.0989 times 10 to the negative 8th meters. So again, we want to make sure we use the right number of significant figures as we had all semester. We've got 3 here, so we want 3 in our final answer. 1.0989 would round to 1.10 times 10 to the negative 8th meters. Okay, it's pretty straightforward. For the yellow region, I'm not going to use yellow because it's a little bit hard to see, but we can see that it's going to equal, we've got this frequency corresponding to yellow, 3.00 times 10 to the 8th meters per second divided by 5.26 times 10 to the 14th inverse seconds. Come back over to our calculator over here, clear that out, somehow clear that out, there it is, equals, open parentheses, 3.00 times 10, oops, see if I can go back, here we go, times 10 to the 8th, close parentheses, divided by, open parentheses, 5.26 times 10 to the 14th, close parentheses, equals 5.703 times 10 to the negative 7th. Again, dealing with the right number of significant figures would equal 5.70 times 10 to the negative 7th meters. Okay, so what's interesting is the way that I've set these up today is that we actually need those two numbers here for the next set of problems here. Okay, so we need to remember that. when we take a look at the next example, we said, okay, in the previous examples, we calculated what was going on. Get out of my letters here. There we go. In the previous examples, we calculated the wavelengths that corresponded to two different types of light. Let's calculate the energy in joules of an individual photon. So we need to remember that the energy is going to equal h times the wavelength. Okay, I'm sorry. What did I do? Oops. Come back over here. Sorry about that. Does not equal h times the wavelength. Equals h times the frequency. Okay. Or we could do it as E is equal to h times c divided by wavelength. Okay, either example will work just fine because as we can see, and we figured this out before, frequency is going to equal c divided by wavelength, or wavelength is equal to frequency divided by c. Either way, okay? So what we end up with here is that we have some previous wavelengths. We've got 1.10 times 10 to the negative 8th meters for our first wavelength. But because we want to play it on the safe side, let's go ahead and use that frequency, 2.73 times 10 to the 16th inverse seconds. Okay, so what we know is for that first one, we know that E is going to equal h times the frequency. We know that h is always equal to 6.626 times 10 to the negative 34th joule seconds times the frequency. I already forgot what it was. Hopefully you wrote it down. Equal 2.73 times 10 to the 16th. So back over here, 2.73 times 10 to the 16th inverse seconds. You can see here your seconds and your inverse seconds are going to cancel, leaving you with joules. So we go over into the calculator, open parentheses, 6.626 times 10 to the negative 34th joule seconds times, open parentheses, 2.73 times 10 to the 16th inverse seconds. And what we get here is we find out that we get a wavelength equal to something really small, 1.81 times 10 to the negative 17th joules. That's not a lot of joules at all. Okay. For the second example, it's the same. E is equal to h times frequency, so it's going to be 6.626 times 10 to the negative 34th joule seconds times, when we look back here, it was 5.26. 0.26 times 10 to the 14th inverse seconds. And so we come back up here. I'm going to do a little cheating here. I'm going to come back here. So what I did was, by doing second entry, what I've done is I pulled up the exact previous entry. So 6.626 times 10 to the negative 34th. And now we just need to change out these keystrokes here. I've gone way too far to say 5.26. 5.26 times 10 to the 14th. And what we get is 3.485, or so we'll call it 3.49 times 10 to the negative 19th joules. And so what's the ratio of these energies? Well, to find the ratio, you take and you divide everything by the smallest. So we take the 1.81 times 10 to the negative 17th, divide it by 3.49 times 10 to the negative 19th. And so if we come back over here, we can take the 1.81 times 10 to the negative 17th and divide it by 3.49 times 10 to the negative 19th. And we see that it's about 51.86. So what we can say is it's approximately 52. So what this means is that the ultraviolet light that we talked about over here, the middle of the ultraviolet region, is about 52 times stronger than that yellow visible light that you could see. And that makes sense because we know the visible light doesn't really do any harm or damage or anything like that, and ultraviolet light definitely will. So now we go to the next example. And so what I've got here is a green line, wavelength 486 nanometers, is observed in the emission spectrum of hydrogen. Calculate the energy of one photon of this green light. Okay, well, so we want to know the energy of one photon, and we've got a wavelength. So now this is kind of like the previous example, except now that we've got the concept of one photon, and that's the energy, except we've got wavelength. So that means we're going to be dealing with E is equal to H times C over lambda this time. Equals H C. Man, I am a mess right now. Hold on a second. Try this one more time. Let's back up. So a green line of wavelength 486 nanometers is observed in the emission spectrum of hydrogen. Calculate the energy of one photon of this green light. Okay, so we're looking for a single photon, and we've got the wavelength, so that means we're going to use E is equal to H times C divided by lambda. There we go. That's what I was trying to do. All right, so we want to try to find E. We know H, 6.626 times 10 to the negative 34th joules seconds. We know the speed of light is 3.00 times 10 to the 8th meters per second. And we know the wavelength in this case is 486 nanometers. Now keep in mind, we've got meters right here. So we need to be able to put that in terms of meters. So we've got a couple of options. We can either say 486 times 10 to the negative 9th meters, which is what I'm going to suggest, or you could do proper scientific notation, move your decimal over 2 places to get 4.86 times 10 to the negative 7th meters. For the purposes of calculations, I don't usually recommend that. So now it's just a matter of coming in and plugging into the calculator, okay? So now what we're going to do is we'll open those parentheses, 6.626, forgive me for a second, times 10 to the negative 34th joules seconds times, so I'm going to say times, open parentheses, 3.00 times 10 to the 8th. Okay, so that's the product of the numerator, and we're going to take the whole thing and we're going to divide it by, open parentheses, 486 times 10 to the negative 9th, close parentheses, equals. And what we come up with is equal to 4.09 times 10 to the negative 19th joules, whatever the heck that means. Okay, so the question is how much, first of all, that's not a huge amount of energy, and it should make a lot of sense because it's only one photon. But to gain us a little bit better appreciation, we've got this follow-up question: how much energy in kilojoules would be emitted by 1 mole of atoms? All right, well, the nice thing about this is that this really is a dimensional analysis, kind of a stoichiometry situation, because what we have is 4.09 times 10 to the negative 19th joules, but it's joules per 1 atom. And now what we want to do is we want to try to turn it into kilojoules per mole. So we can say 1,000 joules is equal to 1 kilojoule, and that would cancel your joules unit. So you're left with kilojoules per atom, and then we know that 6.022 times 10 to the 23rd atoms is equal to 1 mole of atoms. So now your atom unit cancels right there. And so we're left with 4.09 times parentheses 6.022 times 10 to the 23rd, close parentheses, divided by 1,000. And that tells us it's equal to about 246 kilojoules, which also is not a lot of energy. 246 kilojoules, just for perspective, would be the amount of energy that would be required to run an incandescent light bulb for about 40 minutes. what's the wattage? I don't really know. It probably changes, but let's say middle of the road, let's say 75-watt light bulb for about 40 minutes. It's not a lot of time, and it certainly is not a lot of energy in order to do that. So keep that in mind. All right, the last equation that we need is the what's called the de Broglie equation. And what the de Broglie equation does is it relates the speed of a particle and the mass of a particle to the overall energy that that particle involves. Okay, well, we know we can relate energy to wavelength and frequencies, so the de Broglie equation says that we can understand the wavelength of a particle. I'm going to go back to my my black color again. Okay, wavelength is equal to Planck's constant divided by the mass times the velocity of that particular object. Okay, so it's pretty straightforward because we want to calculate the wavelength in meters. Fine. For an electron traveling at 1.24 times 10 to the 7th meters per second. Okay, fine. And we know the mass of an electron to be 9.11 times 10 to the negative 28 grams. Okay. The only thing we need to keep in mind here is that the unit for joules, and I've noted it down here, but 1 joule is in terms of kilograms meters squared per second squared, so we need to make sure we turn that mass grams into kilograms. Outside of that, this is a very straightforward problem because what we're left with is 6.626 times 10 to the negative 34th joules seconds, okay, that's Planck's constant, divided by the mass of this particle, 9.11 times 10 to the negative 28 grams, which is equal to 9.11 times 10 to the negative 31st kilograms, okay, because remember, to go from grams to kilograms, you divide by 1,000, so when you divide by 1,000, you're going to move your decimal 3 places to the left, so that place value gets even smaller, and then we know the velocity it's moving is 1.24 times 10 to the 7th meters per second. Okay, so now it's just a matter of substituting in and solving. So what we're left with is 6.626 times 10 to the negative 34th. Okay, and we're going to divide that by, open parentheses, 9.11 times 10 to the negative 31st, close parentheses, times, open parentheses, 1.24 times 10 to the, oops, didn't register it, times 10 to the 7th meters per second. Now, I'm not so sure that this registered that I wanted to take the whole thing and divide it by the denominator, so I'm going to go back and double check. I want to make sure it says to multiply those two things before we do any dividing, and that's what I thought. So what I need to do is I need to insert a second set of parentheses here. Okay, that's just saying I want the whole numerator, which is Planck's constant, to be divided by the product of those two things. And what we're left with is 5.87 times 10 to the negative 11th meters. Okay, now keep in mind it's got to be meters because we've got meters right here. All right, so we want to keep that in mind. All right, so the second one, we want to calculate the wavelength of baseball. How can we do that? Well, because it's a moving object. A mass of 5.25 ounces traveling at 93 miles per hour. So we got a whole mess of things going on here because we want our mass to be in kilograms, we want our velocity in meters per second. So we need to take our ounces to turn it into kilograms. We need to take our miles per hour and turn it into meters per second. So let's go ahead and start that. We've got 5.25 ounces. We know that there are going to be 16 ounces in 1 pound, and we know that there are going to be 2.2 pounds in 1 kilogram. Okay, and so what we're left with is, for that, we get 5.25 times 1, essentially. So we'll leave it times 1. And we're going to divide that by, open parentheses, 16 times 2.2, close parentheses, equals. Okay, so what we're left with is 0.149 kilograms. So we can now substitute that in. And we have 93 miles per hour, and we want to get it to meters per second. Well, we know that 1 hour is equal to 3,600 seconds. It's really equal to 60 minutes, and 1 minute is 60 seconds. So 60 times 60 is 3,600. And then we know to get to miles in meters, we know that 1 mile equals 1,609 meters. And I just went ahead and looked that up. Okay, so it's pretty straightforward to go ahead and look that up. So what you're left with is 93 times 1609 meters divided by 3,600, and what we have is equal to about 41.6 meters per second. Okay, now once we have these two things in here, we can go ahead and do the calculation just like we did up here, where lambda equals h divided by m times v, 6.626 times 10 to the negative 34th joule seconds, divided by, we know a mass now to be 0.149, okay, and we know the velocity to be 41.6 meters per second. And now you can go ahead and just do that calculation. I'll spare you what it works out to be is 1.08 times 10 to the negative 34th meters. And it should make sense that it's a very, very long wavelength because it's a very large, massive object. Hopefully this video helped you out. Hopefully you got something out of this today, and it's able to give you an appreciation how to do these calculations. And let me know if you have any questions.